So welcome to our lecture about internet security, about weakness and targets. Today we want to speak about the problems for security that arise from design and programming errors. We have already discussed that in the suite of the internet protocols there are a lot of flaws that can be misused for security attacks, for break into systems, for modify data, for get insight into data. We have seen that one can attack passwords and accounts for breaking in. One falls this type of attacks, one needs information about the operating systems and the versions of the programs and systems that run on the victim's IT system that attacker wants to attack. All this is dangerous. Today we want to concentrate on programming error. Beside of the weaknesses of this TCP IP layer, poor design, not good syntax checks, other problems in programming in the network applications can also be misused for attacking a system. Because this network applications that use the internet for communication, so via the internet one can try to get to cause a denial of service attack or to provoke that the system does something other than it originally was designed for. So in this lecture we will discuss some typical errors, 3 errors, which I want to introduce to you, which often happen during the phase of design and programming. For example, buffer overflow. Buffer overflow in several applications is a typical design error that can be misused for security attacks. We see insufficient syntax checks, that there are memory designed resources allocated, and it's not checked whether the data that are stored in these resources fit into the space of this data. So insufficient syntax check is a typical programming error that makes it possible to attack systems. And at the end, I want to introduce so-called race conditions, attacks that are possible if in the right moment an attacker comes in with certain command so that he can perform some programs with root rights. There are more examples particularly programming errors concerning the World Wide Web. We have 2 extra lectures about weaknesses of the World Wide Web. So more of these design errors we will discuss later in 2 other sections. So let's start with having a look to the really dangerous attack of so-called buffer overflow. The buffer overflow is quite easy to understand. To perform this in a sophisticated way is very difficult. The basic idea is that there is certain space of the programming memory reserved for various variables that are used and where data are assigned during the computation. Often there is no careful check whether the length of the corresponding data exceeds the maximal length of the reserved memory. Yeah, there is a reserved memory for a variable, and the user, if they are able to give in data that are longer than the space that was reserved for this data, then there is some overriding of unreserved space. So as a result, neighbor fields of the reserved space are overwritten. The basic idea of such buffer overflow attacks are that provoke and misuse such an overflow from outside. So cause a system to write something into space that was not considered to be open from outside, And then we will see different types of attacks, simple denial-of-service attacks only to disturb the work of the system, up to a very sophisticated, serious buffer overflow attack, where this overwritten information gives programming code, bad programming code from the attacker. So the idea and the reason for such buffer overflow attacks are possible, the reason is simply a poor programming style. People reserve space and they have no introduced techniques to check whether data that are input fit into this reserved length. So the reason is the maximal length of the external data are not checked. If the maximal length is checked and it's checked that it agrees with the length of the space that's reserved, no problem. Overriding is not possible. Overriding of other parts of the memory is not possible. But if this check is missing, for example, due to make performance, increase performance speed or others, if the check is not in, then it's possible, if there is a longer input, that memory space is overwritten, that's not assumed to take this data. So here, this is a simply picture, one can understand the buffer. This is a reserved buffer, and you see the data that are placed into the buffer is much longer. And here, in this part, we have this overriding of the buffer. And here can be placed some nonsense data. So we will see a denial-of-service attack, or it can be placed. Data, for example, performable code. So let's start with seeing what are the preconditions of such a buffer flow attack. What needs the attacker know? What needs he know to successfully perform such a buffer overflow? First, he needs to discover this programming error. He needs to find out in which place in the program there is a mistake that's possible to put in longer data than the reserved space. Then, of course, this buffer the attacker wants to override needs to be accessible from outside. Otherwise, he or she is not able to place bad code in it. And then, this is the main failure, that this buffer is not the length. There are no length controls for the input data for this buffer. So these are the preconditions for a successful buffer overflow attack. And let's start with showing you a simple example, a simple attack scenario, which is a denial-of-service attack. The idea here is that such a buffer is overwritten with senseless data. So with senseless data, and definitely this will disturb the programming, the performance of the program of the victim, and it brings out service out of order, cause some undefined situation, or leads to a breakdown of the system. Here is a simple example of such an denial-of-service attack on a web server. There is here this space that's reserved for giving in an URL, and the attacker gives a much longer data into this URL if it's asked to type in URL, so that all this space that comes here is overwritten, you see, with useless data. And this causes some problems for victim system and is a denial-of-service attack. Let's have a look on a more serious buffer overflow scenario. It's the so-called controlled buffer overflow. Here the idea is that the buffer is manipulated in such a way that executable code is placed there after overriding. Not senseless data. This calls only denial of service, like in the simple a buffer flow attack. Here in the controlled buffer overflow attack, the overwritten part, there is placed some executable code. So victim systems execute this code with respective privilege of the process that's running. In case of server process, this is with root rights or administrator rights. And this makes this buffer overflow so serious, because if it's possible to place executable code, then often there are high rights, root rights, administrator rights available to run this code. In the consequence, the victim systems can be arbitrarily manipulated. The work, the result, what's doing is the service that's provided can be arbitrarily manipulated. But one has to say it's very difficult. It's very difficult to find this, okay, but to place exactly executable code in the sense the attacker wants to get changed the work of the victim systems, it's very difficult to implement this. So it really needs big knowledge. But the problem here, too, is you can find examples of such very serious programs in the internet, so that even people without this experience can access such very sophisticated programs. Here is the same example I gave before, but now you see there is not useless data, senseless data. Now there is executable code. And it is placed when in the URL buffer there is no length check. So if the system accepts such kind of input. In the most cases, here comes the explanation why it works. In the most cases, this affected memory is organized as a stack. Sometimes it's a heap, but in most cases it's a stack. And if you remember how operating system administrates such stacks, it becomes the idea becomes clear for such controlled buffer overflow attacks. In contrast to other storage domains, like for example in text domains are read-only, or in data domains there is no executable code allowed. Here in a stack, it is possible to write during the runtime of the program. This is of this special data structure. It's needed that this is possible to make the program work, but if it gets into wrong hands, you immediately understand that this can be misused. It is in a stack possible to write during the runtime of the program. It's possible to place executable scripts and comments in a stack. So this is not possible with text domain, it's not possible with data domains, but with stack it is. Now remember how such a stack is designed. Stack consists of a return address to jump back to a certain position after finishing the subprogram. Subprogram that's organized by the stack, then there is a return address so that after finishing the work of the subprogram, the system can jump back to the original program. The domain for parameters in the stack are memorized, are stored. There is a domain for the parameters which are consigned to the subprogram. So the stack is a data structure to support execution of a subprogram, and if the subprogram is executed, then by means of the jump back address, a system knows how to jump back to the original program. The space for the local variables are released after return. So the stack is a data structure that's only provided when a subprogram should be run. So this is the organization of a stack, and the idea that for such buffer overflow, such buffers are typically organized like stacks, and now the idea of this controlled buffer overflow is to override the local variables by input from outside. And the intention is to change the return address. To change the return address. And if this is possible, the attacker can control what's done after performing this subprogram. So the return address, that's the idea, does no longer show a point to the original program. It points to the overwritten buffer overflow, to a buffer domain, and to the executable code that is placed in the overwritten buffer. Yeah, that's the idea. Change the return address by overriding the buffer so that the program afterward does not jump back to the original point and the original program. It jumps to the start of the executable code that's placed in the buffer overflow. In the consequence, after return, the process executes the code that is located in the overwritten buffer domain. It executes the code of the attacker with the rights of the original program. So here is a picture, the stack of such a program. There's memory domain for the local variables of this subprogram, and then there is a return address and the parameters. And if it's possible to manipulate the stack by means of buffer overflow, you see the return address is overwritten. The return address is overwritten by an address that does not point to the original program, which points to the executable code of the overwritten buffer. So this is a controlled buffer overflow. So the attack programs for such controlled buffer overflow are extremely difficult, because you need exactly to know how the stack is organized, where is the return address placed. You have to replace this by an address where the new overwritten code is given in. So it's very difficult to design, so one needs real knowledge, expert knowledge to perform this. But over the internet, one can easily access such very sophisticated buffer overflow malware. And this makes it difficult because now all the people that does not have such an expert knowledge to be able to write such a buffer overflow attack, they can perform such a buffer overflow attack by means of the malware they find in the internet. So here's a scheme of the buffer flow attack program. Code a program that should be executed in victim system, then create a buffer that contains beside of the program code also bytes. For example, NOP comments if position of buffer in memory is not exactly known, and then allocate the parameters that provoke a buffer overflow, and finally start the attack. So this is what attacker has to do when he or she wants to perform such a buffer flow overflow attack. And the simple reason is that in the programming, in the design of the program, the length check is missing, the length check for data that are placed into a buffer. So here's an example of a buffer overflow attack. The system under consideration is an IRIC system. It's developed by ZGI, by Silicon Graphics. The buffer overflow is provoked by processing parameters in the def command. The def command works, and this is dangerous, it works with the root writes and starts the shell, which also has root writes. Here is such an example. You can have a closer look at home to it, but to show that it's not only theory, that's really possible to perform such attacks. So buffer overflow attacks are really dangerous For example, because here you can manipulate and can get started attacker's code with root rights on a victim system. And then you can create damage or break in others. Let's continue with a second example of a defective syntax check. And this is apart from missing length, checks of external input, which make buffer overflow possible. Same problem, the attacker uses some flaws in the programming, so there is an insufficient syntax check of inputs. So the syntax checks are executed by parsers. So the parser is responsible to analyze the external byte stream and to separate the commands from the parameters. So this is the work of a parser. And the syntax check means that for a certain rule, the parser is able to recognize and to know what's the command, what's parameter. So they are really important, these parsers, but like other software, these parsers also have mistakes. They have problems, typical problems with special characters. So on the basis of such a defective syntax check, the attacker is able to take some advantage of an unwished side effect of an application or of the operating systems for misusing it for his bad purposes. And the core, the reason to be able is he can misuse special characters. Special characters because there is no check, no good check about the effect that special characters have. So let's look to a first example. Here I point to an error in some Apache or NCA web servers, and there are some problems with the character new line, with the character for new line and the character for space, and character for space, which are not filtered out by the parser, and this can have really bad consequences. For example, when you see when the following CGI program is executed. This is a simple program, simple CGI program, and here you see there are these special characters that are not checked, and in the result, the password file with the password hashes will be shown inside of the browser window to the attacker. So with this simple attack, you can get inside to the passwords. Okay, you do not see the password in plain text. You see it as it's stored in the system. So it's the hash of the password. But you know and remember that we have discussed password attacks so that the attacker can really understand and really see the can get out the real passwords out of this hash. The second example of such a defective syntax check and an attack that's based on such a defective syntax check is the misuse of an error in an older news server. In the news server that has the effect that the password file is sent to the hacker via email. It's a little bit more complicated. So here you see what is done. If you go, so that is an interaction with a news server, and in the result, the attacker receives the password file by email. To discuss a third example, so the parser here, the third example is that the parser overlook some special characters like backslash or slash. And of course, these special characters have a meaning for many systems. So this could be, for example, interpreted by a web server as a command to change into higher directory. So thus the attacker is able, if there is not performed, if the syntax check is not performed correctly, so the attacker is able to break out of the virtual root directory on victim system and get access to other directories and can spy out hard disk and data. Another error that often occurs when the syntax check is not performed correctly is that these special characters, the straight line and the semicolon, are overseen, are overlooked, are not correctly recognized. This could force the operating system to arrange an output redirect to start another program. So here you see that simple mistakes in parser for syntax checking can have bad results. Of course, the attacker needs to know. The attacker needs to know the weakness before he is able to make use of it and using it for an attack. The last example of such an design error in programming, I want to mention an attack family that's called race conditions. Here the idea is the following. During processing, the programs reserve resources like data files, memory space, interrupts, and so on and so on. If these resources are insufficiently protected against an abuse, an attacker program which starts in the right moment can get access to these resources. So here, for example, access to temporary data files. You know that in the temporary data files, all the data are stored that are needed to perform a program. And if the program is finished, if the result is computed, all this temporary data are deleted. So the temporary data often are very interesting data. If you have, for example, business computation in mind or some others, so all the data that are analyzed are stored in such a temporary file. The access to such temporary data is often possible without special privileges. And this is a problem. In the temporary data, you see a lot what you cannot see after the program is finished and what you cannot see before the program is finished. So here, the idea to try to get access to the temporary data is really dangerous. So data can be read in the temporary memory. They can even be manipulated for generating some side effects of the application. So what kind of side effects? This depends, of course, from the application. So whether it's only the idea to steal data, or whether it's the idea to manipulate data to influence the final result of the program, or others. This is very dependent from what is the goal of the attacker and what kind of application is attacked. So here's an example for such an attack that belongs to the family of these race conditions. So the idea is sending an FTP command with root rights. The reason why this works is that various FTP servers do not correctly distinguish between two interrupts, between the interrupt SIG-pipe and the interrupt SIG-URT, which may be sent from the client. The SIG-pipe command that finishes a session spontaneously. That's Control-C. And the SIG-ORG command that cancels current active data transfer. That's the Control-D command. The SIG-pipe, this is finishing a session spontaneously, the Control-C. SIG-pipe causes a change to user root and finish the session after some administrational task, for example, closing a log file and others. SIG-URG finishes the current data transfer and jumps back into the main loop of the server program, which is waiting for new requests from client. So, and here comes the idea to misuse this mechanisms. If the attacker is able to send a SIG-URG command in the right moment, and the right moment, this is where the name race condition comes from. After SIG-pipe causes a change to the user root and closing the log file, then the attacker is able to send FTP commands with root writes afterwards. Because here in the right moment, the SIG-pipe is in the causes a change in the user root, so system is in user root, is performing some administration task, and before finishing this administrational task, the SIG-URG command is given in. So in it needs to be exactly in the right moment, and then a system is able to afterward perform FTP commands with such root writes. So here the race conditions with interrupts. We have the FTP server that's waiting for new data and input. Then data says, okay, perform SIG-pipe. SIG-pipe starts to perform changing back to user root, close log file, finish session, and then immediately the SIG-URG handler started is that jump back to the server program, which is waiting, but now with the root writes, which is waiting for new input, and then the attacker is able to place bad content in. So these were 3 examples of design and programming errors that have fatal consequences for the security of IT system, and it shows that programmer need to be very careful when designing programs. They have to perform a syntax check, so that's not possible to give to cause from outside, by outside data, to cause some security problem. Thank you for your attention.